Hello class, welcome back to Physical Geology 001A at West Valley College. This is your professor Farida Baksh Musa. Today we'll be doing chapter 7, Metamorphic Rocks. But before that, let's learn what is metamorphism. Just like, I teach my younger kids morph, right? When something morphs means changes, just like a caterpillar changes into a beautiful butterfly. Similarly, metamorphism means the transformation of rocks deep within earth under conditions of heat, pressure and fluids. By the end of this chapter, you will be able to explain the factors that drive metamorphism, describe foliation and rock textures, classify different metamorphic rocks, understand where metamorphism happens in relation to plate tectonics, summarize the processes of regional and contact metamorphism, and recognize the critical role of fluids in metamorphism and mineral deposits. So, what is metamorphism? It's when a metamorphic rock is formed when existing igneous and sedimentary rocks change because of high pressure and temperature. And we've studied that in our rock cycle too, right? How the magma cools down, forms igneous rocks. Igneous rocks get weathered and forms sedimentary rocks. Sedimentary rocks and igneous rocks, when they undergo high temperature changes, they undergo metamorphism to form metamorphic rocks. And we'll be studying about the textures, the way to identify them, just the environment that they form, what was the parent rock, what are the different types in which a rock can be metamorphosed. So there's contact and thermal. So we'll study all of that in today's lecture. So let's get started. Okay, so what controls metamorphism? Metamorphism doesn't happen randomly. It depends on 5 key controls. Parent rock composition determines which new minerals can grow. Temperature. Minerals remain stable only within certain ranges. Clay transforms into mica about 200 degrees Celsius, while quartz persists up to 1800 degrees Celsius. Then pressure. Confining pressure densifies rocks, while directed pressure aligns minerals, producing foliation. Fluids, mainly water, speed up reactions and transport ions, playing a major role in mineral changes and metamorphism. Time. Mineral growth is incredibly slow, about 1 millimeter per million years, but tectonic processes act over tens of millions of years, giving reactions time to complete. Foliation and rock textures. Foliation is one of the most striking features of metamorphic rocks. If you see this. Under directional stress, platy minerals like mica line up perpendicular to the pressure, creating layers or bands. The 4 key foliated rocks. Slate, very fine breaks into sheets. Phyllite, silky, sheen, wavy layers. Schist, visible mica and accessory minerals like garnet. And gneiss, alternating light and dark mineral bands. Now, non-foliated rocks form when there's little directed pressure, such as quartzite from sandstone, marble from limestone, hornfels via contact metamorphism. When rocks almost melt, they create migmatite, blending igneous and metamorphic textures. Let's talk about metamorphism and plate tectonics. Plate tectonics explains the main settings of metamorphism. Continental collision. Sediments buried to 15 to 25 kilometers become schist and gneiss. Examples, the Himalayas. So lots of pressure and that changes the rock type. Spreading ridges. Seawater circulates, altering basalts into greenstone or green schist. Subduction zones. Cold rocks under high pressure form blue schist. Rare exposures like the Franciscan complex near San Francisco show these rocks at the surface. Contact metamorphism. Magma intrusions heat nearby rocks, forming marble, quartzite and hornfels. Volcanic arcs. Higher geothermal gradients lead to higher grade metamorphism closer to surface. Regional metamorphism happens when rocks are buried 10 to 20 kilometers beneath the mountain bed. These zones often extend over thousands of square kilometers. Geologists identify regional metamorphic zones by index minerals like chlorite, which is low grade, biotite and garnet, medium grade, and sillimanite, that's high grade. A great case study is Nova Scotia's Maguma terrain, metamorphosed during the Akkadian orogeny around 400 million years ago. In the southwest, rocks were heated above 700 degrees Celsius down to 25 kilometers. sillimanite zone. Towards the north, low-grade chloride zones reflect shallower burial. This pattern occurred because crust under the mountains thickened and sank into the mantle, which is the concept of isostasy. Later, erosion uplifted the once buried rocks back to Earth's surface. This process explains why deeply metamorphosed schists and gneisses are exposed in eroded mountain ranges worldwide. Contact metamorphism and geothermal processes. Contact metamorphism occurs when magma intrudes cold crust. The heated margin surrounding the intrusion is called an areole. Around small dikes, areoles may be centimeter wide. Around large plutons, areoles may extend tens of meters. So what are the rock changes that are happening? Mudstones change to hornfels, limestone to marble. These are all sedimentary parent rock. Sandstone sedimentary rock becomes a quartzite or metamorphic rock. But remember, heat isn't the only factor. Crystallizing magmas release water rich in dissolved elements. Fluids spread into fractures depositing quartz, veins, sulfides, and even metallic ores like gold. If groundwater circulates around the intrusion, it can chemically alter rocks far from the contact. When metasomatism involves hot fluids, it's called hydrothermal alteration. One special case is the scar formation, where fluids react with limestones to produce garnet, pyroxene, magnetite, and copper-bearing minerals. Skarns are economically important ore deposits worldwide. So how do metamorphic rocks reach the surface after being formed at 20 kilometers depth? The answer lies in geology's vast timescales. Mountains rise, thickening the crust. Deep burial drives metamorphism. Erosion removes the overlying rock. The crust rebounds upward, exposing once deep metamorphic rocks. These processes are continuous, recording Earth's relentless recycling of materials. So to summarize it all, metamorphism is controlled by composition, temperature, pressure, fluids, and time. Foliation forms under directed stress. Key foliated rocks include slate, phyllite, schist, and gneiss. Non-foliated include hornfels, quartzite, and marble. Example, hornfels. These are non-foliated rocks, and these are foliated metamorphic rocks. And this is a serpentinite, which is California state rock. Almost all metamorphism is linked to tectonics, collisions, ridges, subductions, volcanic arcs, and magma intrusions. Regional metamorphism occurs deep under mountains, recorded by index minerals like chlorite, garnet, and sillimanite. Contact metamorphism around intrusions can form hornfels, marbles, and ore-rich skarns. Finally, processes like metasomatism and hydrothermal alterations show the dynamic role of fluids in redistributing Earth's elements. Metamorphic rocks are not just altered stones. They are time capsules of Earth's depths, bringing deep geological stories to the surface for us to interpret. Thank you so much for joining me for today's lecture on metamorphism. If you have any questions, please join my office hours on Fridays, or send me an email via Canvas or via my personal email or my WhatsApp or my message to schedule another call to solve your doubts. If you have any questions with the study questions or the lecture questions, please feel free to reach out to. Good luck, and I'll see you in the next lecture. Bye-bye.